Hi, welcome to another video. So this one's an update on the OV7670 camera. That's the back of it. I made a few mistakes in the other video, so I'm redoing it. Just the cheap $2 camera. This is the non-FIFO version, which also means it doesn't come with an oscillator. So I've got a video on YouTube. I've used this Linear Technologies device down here in the corner. It's got a 10k potentiometer. Have a look at the video. I'll try and put a link. Linear Technologies LTC1799. Now that's an adjustable oscillator. Runs on 2.5 to 3.3 volts, and it runs from frequencies from 1 kilohertz to 33 megahertz. So that's what I'm running this camera on today. So why I'm redoing the video, as a YouTube member, mine Thomas, pointed out, I'd previously looked at these signals, approximated the value of these clock signals up here. So if I expand this out, I measured a few, changed the horizontal time base, and then approximated how many clock cycles I must have up here, and I thought it was over sort of 500-600, but it wasn't. I've just connected the camera today, recounted them. I've got roughly 480 clock cycles here. So this is the HREF horizontal sync, and you get a rising edge at the start of every new line, and because I've set this camera up at VGA mode, I must therefore have 480 rising clock edges. So I've got 480 lines there, and in between each line you can see this pulse down here. This is the vertical sync, so every time I get a vertical sync pulse, that's the start of a new frame, start of a new picture. So with my external oscillator running approximately 18 or 19 megahertz, I've got a line frequency of 1.68 kilohertz, so 1,686,000 lines a second, which gives me just over 3 frames a second. Right, so I've done a quick sketch. This is the camera, that's the camera chip behind the lens, and all that's on this board, a couple of regulators for the chip, I believe something like 2.5 and 1.8 volts. So you get a ground, 3.3 volt supply. On my Pic32 I've got this communication line wired up to I2C1. So on the Pic32 that's RA14 and RA15. I believe the clock spec says 400 kilohertz for the communication. I found it works from 100 kilohertz to 400 kilohertz. This SCCB interface, it's actually the same as I2C, but if they called it I2C they'd have to pay the royalties. So you've got a clock and data. This is the clock input for the device, the external clock. They quote 10 megs to 48 megahertz. Now I initially ran this camera on my oscilloscope wave generator, and my square wave only runs up to 10 megs. So I switched to sine wave, which does run up to 20 megs, and this camera worked happily with the sine wave input. So sine wave or square wave. This Linear Technologies oscillator I've got is square wave, and as I say it's running about 18.5 megs. These are the outputs. So because I miscounted on the scope, I had some of these were named wrong. But so you've got 8 lines of data, 8 bits, and mine's on port A. You've got the pixel clock, which with the camera slowed down 7 or 8 times, this pixel clock is 2.5 megahertz. Then you've got the HREF, so horizontal sync. So you've got one new line there, new line, new line, new line. And in VGA, so 640 by 480, I've got 480 lines. And then you saw on the scope, new vertical sync for every frame, start of every frame. So just to make things clearer, if we zoom in on this pixel clock, which you saw there, if we zoom in, look at a couple of the bits. On each rising edge of the pixel clock, when the pixel clock is high, 8 bits are shifted out of the camera, 8 bits of data for the picture. And on the second rising edge, the second 8 bits, so the second byte is shifted out. Now, although you can alter this pixel clock, you can start and stop it. Generally, the pixel clock is left running. You've got to capture the first 8 bits when the pixel clock is high, and then the second time it's high, capture the second 8 bits. And that can only be done when the 8ref is high. And to explain why my picture is a bit dodgy on my screen, which I'll show you in a minute, so with my camera slowed down by 7 times using the clock prescaler, the pixel clock is still running at 2.5 MHz, which is too fast for my Pic32 microcontroller running at 80 megs. So in that 2.5 MHz or 2.5 million times a second, I would have to capture one of these rising edges, and before it turns off again, store the first 8 bits, so it's byte 1 from port A, capture the second rising edge, store the second 8 bits, so it's byte 2, so all of them together, so byte 1 all with byte 2 to give me 16-bit video signal, and then display it on my TFT 70 screen, which is reduced to 640 by 480, and it's a TFT running a 16-bit with microchip's parallel master port mode. So essentially, with a pixel clock at 2.5 megs, my Pic32 running at 80 megs can't capture the pulse and do something with it twice with a pixel clock of 2.5 megs. So what I've had to do is bodge the code to get a picture on the screen. So what I'll do is show you the relevant bits in the code. I'm using Microelectronica's MikroC Pro for Pic32. So the first bits I'm using I2C1 initialization. You can see I'm running at 100 kHz, and you can see there RA14 and RA15. I'm using a parallel master port, and if you're not sure how to get a 7-inch TFT going, look at my other videos. This video is about the camera. Well, these two parts here, these are the external interrupts. So the interrupt priority and interrupt sub-priority for the two external interrupts that I've got on RE9 and RD0. So this external interrupt here, this is where I tried to capture the pixel clock on this interrupt. Store the first bit of data on port A, wait for the next edge, and then store the second bit. And at 2.5 megs coming in here, the microcontroller would then not run the TFT. I could capture the bits and not run the TFT, or run the TFT and not capture the bits. So I've had to abandon this interrupt, and I'm using this second interrupt. So that's on RE9. So you can see I've got line sync, but that's frame sync. So every frame sync pulse, this interrupt is capturing that pulse, and it runs my TFT. So these are the two external interrupts. So this was the first interrupt that didn't work, and I'll try to capture the pixel clock. I had a counter counting from 0 to 1, so 2 counts, and on the first count it would capture the data on port A, so the first byte, and then on the second count, so on the second rising edge of the pixel clock, I'd capture the second byte of data. But doing that stopped the TFT, so I had to abandon this. This is what I've ended up doing, so just synchronizing my TFT on the vertical sync. As I say, I'm getting a vertical sync every 3.2 seconds, so 3 frames a second. I capture that rising edge, clear the flag, and introduce a camera flag 1 here. So in the while 1 I'm looking for this camera flag. So this is the while 1. Every time I get the camera flag I run this routine. So 0 the flag, TFT chip select is 0, right to the SSD 1963, so TFT SSD 1963 set address pointer 00 width height. The width and height is defined above, so 640 by 480, and I've got 2 for loops there. You can see height H is less than the height plus plus, and then similarly with the width. Width equals 0, width W is less than the width plus plus. Because I'm not able to capture two lots of data on the pixel clock interrupt. I'm bodging it here, so this is why you'll see the colours wrong. So temp 1 is port A, temp 2 is port A, video equals temp 1 ORed with temp 2 shifted 8 places to the left to give me a 16-bit value, and then just writing the data to the TFT. And then down the bottom, chip select equals 1. So I have to emphasise that's the only way I could get a picture on this TFT. It's not the way to do it. But this Pic32 80 meg microcontroller is too slow. Just waiting for Microelectronica to include the Pic32 MZ running at 250 megs. So before I show you the TFT, I'll run through the camera initialization. Right into this camera, the address is 42 for write and 43 for read. So we're writing, so we use the address 42. There's 201 registers here at least. So I'm just going to scroll through them. If you need to copy them, pause the video and copy them down. Don't ask me to post them somewhere. Unless you've got my TFT running on my oscillator, these codes might be different. So I'll scroll down and just pause the video. Some of these aren't particularly important and some are. So I'll stop at this one, for example. This is the external clock prescaler. I've previously been dividing the clock by 7 times, which is actually 8 to 6, because the divide number here is that number plus 1. So now if you look here, 8-7 means I'm dividing it by 8 times. Have a look at the data sheet. So that's what I'm doing today here, dividing the clock by 8 times. That's important, that register. Then for CIF, QVGA, or RGB, this register is important. You can see here, just got a 4. Don't know if you can see this note over here. So for CIF, 352 by 288, that would be a 20, for example. There's a lot of automatic gain controls for the colours and then lens correction. As I say, over 200 registers. This is the pixel clock divider. So look, putting a 14, hexadecimal 14 in there, for example, divide the clock by 16. I tried hundreds of permutations. No matter what I do, the camera, to have a reasonable picture, the camera needs to be running fast and the pixel clock needs to be running fast. And as I say, this Pic32 is not quick enough. So I understand with some of these registers, they've got a default value, but because I was having trouble with the colour, even if the default value was a standard value, I still put the register in here and wrote to it. So you can see this is one I was playing about with. This is one of the lens correction controls. But then if you adjust that, you need to adjust 4 or 5 other registers. So this is a PLL multiplier for the input clock, you can see. So if you're running on a slower clock, you can use the internal PLL and speed it up. But as I say, I'm running that external oscillator about 8.5 megs today. I think you can see there black pixel correction enable, white pixel correction enable. I think I did adjust that. But really the important registers are the external clock frequency and what video standard you want. Those registers at the beginning. You probably get away with just putting 3 or 4 registers in here, but I've got 201 listed. Right, nearly at the end. As I say, if you want to check these, you have to pause the video. Right, I noticed I'd looked at another site and got these video standards. They were actually wrong in the last video. So you can see CIF 352 by 288, QVGA 320 by 240, and then QCIF 176144. And I've got notes over here. So you can see CIF is common intermediate format. And then quarter video graphics array, and quarter common intermediate format. And what I'll show you, mine set to VGA 640 by 480 video graphics array. And there's my picture. So I've got the camera looking at a black and white cup, and you might be able to see me in the background, just over the top of the cup. That's a black and white cup. So the screen 640 by 480, hence the black line down here. This is actually an 800 by 600 screen. So that's a black and white cut, low light levels, doesn't look too bad. Now if I turn the light on, you can see the colours are wrong. If I move this cup out of the way. So what colour shirt have I got on today? Actually this poor camera doesn't like this light shone at its face. I'm actually wearing a blue shirt today, so you can clearly see the Nikon camera. You can see me. We've got 3.2 frames a second, and the colours are just all off. Actually works quite well as a black and white camera with this messed up code. But with reference to the resolution, I put a cup with writing on there. There we are. So I'm an Aries, born in April. It's a nice resolution, but the colours are off. That RAM, although there's blue coming out, the RAM should be light blue, and around the edge should be darker blue. But as I say, to bodge the code, the microcontrollers are simply not quick enough. But it does give you a usable picture. You can actually see the TFT scanning the frames there. Although it says, well, in theory 3.2 frames a second, I'm not sure that's 3 a second. I don't know, maybe it is. So that's what you get when you try and run one of these $2 cameras with, I don't know, a $10 microcontroller, $200 or $300 software, and the microcontroller is simply not up to it. Anyway, hopefully I've got rid of all the mistakes from the previous video, and hopefully you found this video useful. Thank you for watching.